Good morning everyone. In this video, we can start module 4, that is bandwidth utilization, multiplexing and spread spectra. So here you can study how we can use the bandwidth efficiently, or how you can utilize the bandwidth efficiently to achieve some specific goals. So for achieving the efficient use of bandwidth, we are using a technique known as multiplexing. Okay, here we are sharing the bandwidth between multiple users to achieve the efficiency. So for achieving efficiency, we are using some multiplexing techniques. So what is actually multiplexing? Multiplexing means if we have several sources and they share the same communication medium with minimum or no interference, or how efficiently several sources can share the same communication medium. So നമ്മുടെ bandwidth utilization വേണ്ടിയിട്ടുള്ള ഒരു ടെക്നിക്കാണ് ശരിക്കും മൾട്ടിപ്ലക്സിങ്. ഇപ്പോൾ എന്താണ് മൾട്ടിപ്ലക്സിങ്? മൾട്ടിപ്ലക്സിങ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ സെവറൽ സോഴ്സസിൽ നിന്നുള്ള സിഗ്നൽസിനെ എങ്ങനെ ഒരു പെർട്ടിക്കുലർ ട്രാൻസ്മിഷൻ മീഡിയം, ഒരു കോമൺ ട്രാൻസ്മിഷൻ മീഡിയം എഫിഷ്യൻ്റ് ആയിട്ട് യൂസ് ചെയ്യാം എന്നുള്ള ആ ടെക്നിക്കിനെയാണ് മൾട്ടിപ്ലക്സിങ് എന്ന് പറയുന്നത്. വിത്ത് മിനിമം ഓർ നോ ഇൻ്റർഫറൻസും ഏറ്റവും ലോ ആയിട്ട് അല്ലെങ്കിൽ ഇല്ലാതിരിക്കുന്ന ഒരു കണ്ടീഷൻ ആക്കിയിട്ട് എങ്ങനെ ആ കമ്മ്യൂണിക്കേഷൻ മീഡിയത്തിനെ എഫിഷ്യൻ്റ് ആയിട്ട് യൂസ് ചെയ്യാം എന്ന് പറയുന്നതാണ്, അല്ലെങ്കിൽ ആ ടെക്നോളജിയാണ് നമ്മൾ പറയുന്നത് മൾട്ടിപ്ലക്സിങ്. സോ വി ഹാവ് മെയിൻ 3 ടൈപ്സ് ഓഫ് മൾട്ടിപ്ലക്സിങ്. One is frequency division multiplexing, then wavelength division multiplexing, time division multiplexing. So wavelength and frequency division multiplexing is an analog multiplexing technique, and the time division multiplexing is a digital multiplexing technique. This is the general category, and we have two more, or we have another technique, multiplexing techniques. One is space division multiplexing, that is SDM, and a code division multiplexing, CDM. Also for time division multiplexing, we have two another types, or two another categories are the synchronous TDM and asynchronous TDM. Synchronous time division multiplexing and asynchronous time division multiplexing. Also all together we have space division, frequency division, wavelength division multiplexing, then time code division multiplexing, time division multiplexing, and they are divided into two: synchronous time division multiplexing and asynchronous time division multiplexing. So what is the purpose of the multiplexer and demultiplexer? So we are using two hardware structure for multiplexing process at the center side as well as at the receiver side. Okay, at the center side we are using multiplexer. At the receiver side we are using demultiplexer. That means this multiplexer or mux can take n input signals or n input lines, and they will be combined, and the combined form will share the common communication link by using n channels, and it will reach at the reception side. Okay, at the receiving end we have demultiplexer. This demultiplexer will take the combined signal as input, and it will separate these signals into n original signal or n output lines. So this is the function of multiplexer and demultiplexer. Actually multiplexing is several sources can share the same communication medium with minimum or no interference. For that we are using multiplexer at the one end, and other end we are using demultiplexer. For multiplexing, multiplexer is used, and for demultiplexing we are using demultiplexer. Okay, so in figure you can see n inputs to a multiplexer, and this multiplexer is connected by a single data link to a demultiplexer, and the link is able to carry n separate channels of data. Actually, the multiplexer combines or multiplexes the data from n input lines and transmits over a higher capacity data link. And the demultiplexer accepts the multiplexed data stream, separates the data according to the channel, and delivers the data to the appropriate output lines. I have already discussed this. Next, first category of multiplexing technique, that is frequency division multiplexing. It's mainly used in radio and television set. So we can have a number of signals as input, and by using different carrier frequency, we can modulate all these n signals. Okay. So in frequency division multiplexing, by using frequency, the signals are modulated or multiplexed. Okay. We have n input lines or n input signals. By using n different carrier frequencies, we are modulating these n signals. That is actually multiplexing, combining, and they share same transmission medium. Okay, they are generally used in or mainly used in radio or television set. So FDM, frequency division multiplexing, is an analog multiplexing techniques that combine analog signal, and it uses the concept of modulation because we are using different carrier frequencies for modulating these different n input signals. Okay, so you can see in this figure we have three baseband analog signals. You can see in the figure we can choose F1, F2, F3 as carrier frequencies, and by using that carrier frequencies we can modulate these baseband analog signals. Then combined, it will share the same common medium or transmission medium. That is the process actually happened in frequency division multiplexing. We are using different carrier frequencies for modulating, okay, or combining or multiplexing these baseband analog signals, and the combined form will share the transmission medium. That is actually FDM, frequency division multiplexing. Okay, നമ്മളിവിടെ 3 അനലോഗ് സിഗ്നൽ യൂസ് ചെയ്തു. അപ്പോൾ 3 അനലോഗ് സിഗ്നലിനെയും മോഡുലേറ്റ് ചെയ്യാൻ വേണ്ടിയിട്ട് 3 ഡിഫറെൻറ്റ് ഫ്രീക്വൻസി സിഗ്നൽസിനെ യൂസ് ചെയ്തു. അങ്ങനെ മോഡുലേറ്റ് ചെയ്തതിനെ കമ്പൈൻ ചെയ്തിട്ടാണ് ഒരു ട്രാൻസ്മിഷൻ മീഡിയത്തിൽ കൂടെ അയക്കുന്നത്. ദാറ്റ് പ്രോസസ് ഈസ് നോൺ ആസ് ഫ്രീക്വൻസി ഡിവിഷൻ മൾട്ടിപ്ലെക്സിംഗ്. So at the reception side we have FDM demultiplexing, that is frequency division demultiplexing technique. So combined form, it will reach at the receiving side, and by using the filter we can separate the n channels, and by using the demodulator we can separate the carrier frequencies from this composite signal. Then it will produce original signal. Okay, that is actually demultiplexing. So demultiplexing എവിടെയാ? റിസപ്ഷൻ സൈഡിൽ കമ്പൈൻഡ് മൾട്ടിപ്ലെക്സ്ഡ് ഡാറ്റയെ കിട്ടി, അവിടുന്ന് ഫിൽറ്റർ ഉപയോഗിച്ച് അതിനെ n ചാനൽസ് ആക്കി ഡിവൈഡ് ചെയ്തു. ദെൻ n ചാനൽസ് ആയി കിട്ടിയതിൽ നിന്ന് നമ്മൾ എന്തിനെ മാറ്റണം? ഒറിജിനൽ സിഗ്നൽ കിട്ടണമെങ്കിൽ കാരിയർ ഫ്രീക്വൻസിയെ നമ്മൾ ഒഴിവാക്കണം, റിമൂവ് ചെയ്യണം. ഫോർ ദാറ്റ് വി ആർ യൂസിങ് ഡീമോഡുലേറ്റർ. ഓക്കെ, സോ ഡീമോഡുലേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ F1, F2, F3 ഫ്രീക്വൻസി സിഗ്നൽസ് അതിൽ നിന്ന് ഒഴിവായി നമുക്ക് എന്ത് കിട്ടും? ഒറിജിനൽ അനലോഗ് സിഗ്നൽ കിട്ടും. സോ ദിസ് ഇസ് നോൺ ആസ് FDM, demultiplexing in frequency division technique. Okay. Next category is wavelength division multiplexing. Actually in frequency division multiplexing we are focusing on the frequencies, carrier frequencies, right? Here we are focusing on wavelength. Okay, also in frequency division multiplexing we are using guard bands for reducing the interference in between the signals. Okay, they are no use spectra. Okay, second category is wavelength division multiplexing. It is mainly used in optical fiber communications because optical fiber is fully exploited when multiple beams of light at different frequencies are transmitted on the same fiber. So a typical WDM system has same architecture as that of FDM systems. Here, a number of sources generate a laser beam at different wavelengths. So we are mainly focusing on the wavelength of the signals. Okay. These are sent to a particular multiplexer and which consolidates the source for transmission over a single fiber line. Here we can use some optical amplifiers to amplify the signal. Okay, at the demultiplexer end, composite signals arise and where the component channels are separated and sent to receiver at the destination point. Actually, this WDM is an analog technique to combine the optical signals. So, in frequency division multiplexing, we are focusing on the frequencies of the carrier signals, and in here we are focusing on the wavelength of the analog signals. Okay, actually the range of operation in WDM is 1550 nm range, and there are two types of WDM techniques. One is dense wavelength division multiplexing and other one is quiescent wavelength division multiplexing. And quiescent wavelength division multiplexing, which is mainly used for the short distance connections, and they are not closely spaced, but the dense wavelength division multiplexing, it uses more channels and they are used for long distance communication and more closely spaced. So this is a figure which shows the WDM technique. So we have three different signals with three different wavelengths, W1, W2 and W3. And by using the multiplexer, we can combine all the wavelength. Then it will produce a combined signal and it will share the transmission medium. And at the demultiplexer side, you can see we can filter that combined signals, and then by using demultiplexer, we can separate each individual analog signals with wavelengths lambda 1, lambda 2 and lambda 3. This figure also shows what is WDM, which is mainly used in optical fiber communication. Okay, I think all of you are clear. Thank you.